So first we need our substitution step. So why don't we allow W to equal, well, let's see. The embedded function is what you want to let W be. Here, the function that is nested is this guy here, because sine is a function, but within sine, you have another function, theta squared. So I'm gonna let W equal theta squared. And then as soon as I find W, I want to find dW. And dW would be, well, what's the derivative of theta squared? That'd be 2 times theta to the power of 1 times d theta. And we have something for, so theta squared is going to be replaced by W. I have dW, but I want d theta alone. So what I'm going to do is I'm going to divide by 2 theta. So dW over 2 theta equals d theta. But then watch this trick here. Check this out. This is something that you'll sometimes have to do. If I take the square root of both sides, that becomes theta. But if I square root this, it's going to become square root W, right? I square root this, I square root that, that's what I get. How come I did that little bonus equation? Because over here, I don't want theta. I want W's on the left and theta's on the right. So instead of theta, I can replace it with square root W. So I have dW over 2 square root W equals d theta. And if you want, just do this, watch. Why don't I just write this as 1/2 W to the negative 1/2 power dW equals d theta. You see what I did? The 2 is just 1/2 from the bottom, just 1/2 there. The square root of W is W to the 1/2, but if you move it upstairs, the exponent switches from positive to negative. So now, let's rewrite this here. So this equals, now you know what I'm gonna do? Since we're switching variables like crazy, I'm gonna ignore these integration limits. I'll bring those back at the end of the process. For now, I'm just gonna leave it blank. Now, theta cubed is the same as theta times theta squared. I decided just to separate that for a specific reason. I'll show you why. So theta cubed is just theta squared because theta is square root W. And then theta squared is W times sine of, well, what's theta squared? Theta squared is W times, and then what's d theta? D theta is all of this gibberish right there, 1/2 W to the negative 1/2 dW. But now look, this is good because this is all W's. There is not a single theta in sight. Everything is W. Now I recommend we clean this up a little bit. So integral square root W times W, sine of W. Ooh, now watch, check this out. This is gonna work out nice. 1/2. Look, W to the negative 1/2 is 1 over square root W. And that's so convenient because that actually knocks out that right there. And you see that 1/2, let's move that outside the integral. So that's in the front. Now all that's left is W. And then sine of W, and then dW. So now we are ready for our, our parts. Now we're ready for the parts. And then we set for parts that we wanted to go U, du, v, dv. And then where the dw is always part of the dv, and just squeeze it in right there. Now it's just a matter of here. This is a function and this is a function. One of these functions is gonna go in for u, and then the other one is gonna go in for dv. Always, always, always. That goes in these two slots. Not these, nuh-uh. They go here and here. Which one of these do you want to drop in for u? And which one of those goes in for dv? Well, the one whose derivative would eventually take you to 0, that is what you want to let u be. So I think you can see that w is what you want there. And then sine would go in here. Okay, now let's see. The derivative of u is du, so the derivative of w is dw. Make that look a little nicer. Now look, if that's dv, then what was v? I need something here that the derivative of this is positive sine w. Well, I would need negative cosine w, right? Because the derivative of cosine is negative sine. So the derivative of negative cosine would be positive sine. So now we rely on this here. So let me just leave that right there, I suppose. And so watch, this equals 1/2, now parentheses, and all this integral, all of that gets replaced by this. So I need u and v, which is u and v, so that's these guys right there. Those two would go right here. And then minus integral v du. So that's v du. So that'd be negative cosine w dw. Negative cosine w dw. So thank you, parts integration. We're done with you. So we did a substitution with w's. Then we did parts substitution. So now we're here. Let's clean this up. How's about we make that double negative positive? That negative could escape. It essentially makes all that positive. And you know what? I think we're ready to finish this problem. We have 1/2 negative w cosine w plus, what is the integral of cosine? That would be positive sine w. I'm not going to put a plus c because we actually have limits of integration. But now that we've actually done the integral here, now we're ready to turn it back into thetas. We started with thetas. At some point, we should go back to thetas. So this is 1/2 negative. Instead of w, consider the original assignment. W is theta squared. So that's theta squared times cosine theta squared plus sine of theta squared. So now that we're back in terms of thetas, we can welcome back into our life these original limits of integration. So my professor used to do like a little bar where that bottom number goes here, and then that upper number goes up there. And so now what we're gonna do is this. I'm gonna write this all over again, but all the thetas become that. And then it's gonna be subtraction, and then again, all of this, but instead of thetas, it's gonna be that. And this is what it looks like. So I took square root 2 pi, plugged it into all the thetas, and that's this part here. And then it's always subtraction. And then I took that number, plugged it in for all the thetas there, and that's that. If you want, you can go here. Just make sure that your calculator is set to radians because you have pi's and stuff all over the place. So this is what I got here. But again, you don't have to do all this. You can just type this in there. But I think this will give you a decimal. I don't think it'll give you this exact number. So it depends on what the professor wants. You know what else you could do? You don't have to type all of this in at once. You could type in just pieces of that into here to get an exact number. Because I'm pretty sure that if you type all of that as is, not only is it kind of hard to do, but you might get like a decimal instead of this exact number.